Alright, moving forward with powers. Our learning goal again is exponent laws and order of operations to solve exponent problems. And now we're getting into the latter bit here, solving exponent problems involving area, volume, and surface area. You can practice area and volume. We're going to key in on surface area today, one of those applications, because we haven't really reviewed area and volume, but you will see some problems like that, and the exponents are used in the same way. First up, we've got surface area cube, and the example we've got here is that we're looking for the surface area of this Rubik's cube if each cube in it is 1 centimeter by 1 centimeter. So this guy is 1 centimeter, and this guy is 1 centimeter. So the whole side of this cube would be 3 centimeters, and each dimension would be 3 centimeters. So that's just kind of the information we're given in the question. But now we're asked to think about surface area. And if we remember, surface area is the total area of all the sides. In any figure, the total area of all the sides in the figure. We are going to spend some time later on in the course looking at surface area. But for now, that's what we're talking about. So in this case, we have 6 sides. So we would have 6 times the side area. Right? Because we're just asked for the surface area, we're asked for the total. So 6 sides, 6 times the side area, which would be 6 times side squared. This is kind of our generic formula we could use for any cube, and that would work, right? If we're talking about the surface area, all the sides of the cube, we've got 6 sides, each one is side squared. So in this case, 6 groups of 3 centimeters squared, because that's our side length, equals 6 times 9 centimeters squared. Our total surface area of the Rubik's Cube would be 54 centimeters squared. Alright, pause it, write that down, try it out, see what you can come up with. Another place we're commonly going to see exponents being used is in bacterial growth or exponential growth. So I want to look at an example here. Just listen. 5,000 billion bacteria in one day is what they said. If at that rate, at that specific rate, you can check out the video there online if you couldn't hear it. But we've got actually a different example that we've set up for ourselves here. We've got an initial population of 100 bacteria. The question tells us that it's doubling every hour, and then we're asked how many are present after 3 different time periods. I'm going to strongly encourage you to set up your work like this. You could kind of start playing around with the numbers and you might get somewhere, but really what we want to figure out is we want to figure out how to get to the repeated multiplication and then eventually the exponential form. So you've seen a table like this initially when we talked about Alice eating cake. But here in this case, after 0 hours, we have 100 bacteria in our colony. After 1 hour, it's going to double, so we would have 200 bacteria. 2 hours, we'd have 300. That's not doubling, is it? 2 hours, we would have 400 bacteria. 3 hours, we'd have 800 bacteria. 4, 1600. 5, 3200. And then it asks us about n, and we'll come back to that in just a minute. But what we really want to do with these numbers is we want to show this as repeated multiplication. So initially, we're just starting with 100. Next, we're taking that 100 and we're doubling it to get to 200, right? Those are equal. And then we're taking that number, and we can really double that again. So we can take our 200 and double it. Take our 400 from the previous question and double it. So there's kind of, I'll maybe bracket off the previous answer. And then we had our 800, which was this, and we're doubling it. And I know this may not be intuitive, but I'm just intentionally trying to do it to show the repeated multiplication. So here's our, with the 4 2's is our 1600, and then we're doubling again. So the reason that's useful for us is we can use it to show exponential form. 100 times 2, squared. And look at that, it's squared after 2 hours, it's 2 to the power of 1 after 1 hour, and now we see the pattern. Now it all kind of fits together because we laid out our work. Changing colors on us, but you see what's going on here. we laid out our work nicely to see this pattern. This was 3, pardon me, this is 4 hours, 100 times 2 to the power of 5 after 5 hours. And you can do the math, you can check that on your calculator, make sure it works. Notice this exponential form. Remember, if we had 2 to the 0, then anything to the power of 0 is equal to 1. So 100 times 1 is still 100. Right? We still have a population of 100 at 0 hours. If we're talking about n hours, then we could just use the exponent n, right? And n would kind of be any number of hours. Alright, and that's going to become useful depending on the kinds of questions we're asked, depending on the kinds of things we need to do. There it is, you guys. So take a look. Make sure you can get your head around this, and make sure you can get your head around how that translates to the exponential form. That's what we're really interested in. Those are difficult kinds of questions, but when you see this, think about this, right? Think about your setup, think about your table, try to get to repeated multiplication, and get to exponential form. Good luck.